Okay, I have some sort of mechanics, logistics to talk about. So.
All right. Okay. I will make a very secure one.
All right. So let's get started. I'm Raz again. So welcome to the second week of Scalable Data Science. I wanted to cover some mechanics. The course has sort of evolved quite a lot. We have over 50 enrolled and observing students from 4 countries now. So we are sort of broadcasting it on YouTube for those in London and India. So those who are currently live from Wellington and New York City may ask questions. There's only a couple of you. If it gets too loud, then maybe please mute your microphone on your end because I can't control it. Okay, so this is again the course URL, and what we have now is course materials. I'm sort of working on various versions of the course material. So the browsable, uploadable worksheets are going to be posted here. Like, for example, you can go to week 1, and this is just pure HTML code, okay? This you can browse without necessarily having internet connection, right? But some things may not load, for example. And it's, yeah, but you can import it to notebooks in other future cloud instances. So it's sort of a nice place to come and go. And it's very straightforward to get this kind of HTML. All you have to do is go to wherever you want. And let's say we are going to be, you guys want to clone week 2 shortly, but all you have to do is basically go to your whatever worksheet you're working on, go to this icon file and export, and you can export in 3 forms: DBC, archive, source file, and HTML. So if you click HTML, then you can actually just export your notebook in HTML. And that's exactly what I've posted here, right? So this is just in my web page, not quite, where is this one? Oops, there we go. So this is just in my homepage, right? So, and I simply exported the HTML and pasted it there. So the nice thing about this is you can play YouTube videos here and so on. Of course, you won't be able to evaluate cells, right? To evaluate cells, you need the notebook to be running in the cloud. Okay, so let me close this. So that's what these 4 worksheets are. I'll post the video with the lab if you want to see it. The course has a Git book. I'm still battling with Git book because I have to write some code to parse the output of the source code of the notebook so that it's GitHub Markdown and Git book Markdown compatible. Okay. If you didn't understand any of it, don't worry. We basically are writing a book as we go along. Okay. But parts of the books will not be visible right away. Okay. So this is essentially the Git book. The nice thing about Git book is anybody can read. It's device independent, so you can sort of browse on a cell phone and things like this. So essentially, here is a Git book, current version of the Git book. Don't read from here because this is constantly being updated and troubleshot. So you should be able to see, the Git book version of it here. So the idea with projects is we were going to hopefully publish a book, and we are publishing it as we're doing it. So when you do your projects, they will be actually separate chapters, right? So especially those who are enrolled have no choice to do a project, but it can be theoretical too. You don't have to be coding if you don't want to, right? That's some very new details. The deal with students who are observing, and you can propose a project around the break. So the 3 weeks break we have is when both enrolled and observing students will propose projects. I will be more selective about choosing projects from the observing students. But the idea is that some of the observing students actually know more Spark than I do. So the plan is I will learn from them, from their projects, and so will the rest of the world. That's sort of the idea. Now, let me go back to How to make this thing go away. Hi. So let me go back to the sparkapache.org community HTML page. This is actually the Spark community around the world. I decided to make the course essentially a meetup, a Spark meetup simultaneously, okay? This is both a physical meetup and a cyber meetup, right? So these are all the meetups all over the world. There's one, the Bangalore Spark meetup is quite active. There's one in Auckland from last year. Of course, the Bay Area one is kind of huge. So we just got the Christchurch Apache Spark meetup this morning. Okay, because, sorry, I keep touching this thing and I don't know how to make it disappear. I have to sneak in from the bottom, okay? So this is the Spark meetup page. Please join the meetup because I'm going to be doing most of the communication through the meetup because we have a lot more observing students than enrolled students. And it's a lot easier to make discussions here. We can have other members from Auckland already joined, people from California already joined. So please join so that when this course is over, you will have a community to support you, right? And okay, so, and I think we will have an organizational meeting. This is not a requirement for those who are enrolled, but we'll have an organizational meeting sometime in the first week of the break to decide how we want to run this and maybe get some free pizza from some sponsors or something. Okay, that'll be nice. All right, so here is, I'll show you another place where we're populating pointers to potential project ideas. So if you go to Scalable Data Science Work, and there's a notebook called Potential Projects. So here is essentially a list of pointers to potential course projects. Is there anyone here who doesn't have a Databricks cloud account because they just came in out of? Okay. Oh, Shinichi. Can you hook him up, Siva or Paul? Okay, so here's a list of pointers to potential course projects. It's kind of nice. I can see a lot of people are seeing it right now, right? So we will learn to collaborate actually, and we can allow subsets of people to actually manage and edit worksheets. And so here, I basically went through all the ACM communications except 8 so far in the last 3 or 4 years. And I scanned it manually and just pulled out various projects that will be of interest, okay? And it's not complete yet, but I'm just adding things. Also things from current affairs and whatever. So here are some theoretical projects. Some of them are more relevant than others. So here are some applied projects. There is mostly sort of to get you started, there are links to various ACM communication articles. So it's a high level overview. So you can slowly start being steered into what the problem is about. And then you have to, of course, chase the articles that are quoted in these, in these high-level ACM communication papers mostly. Okay, so there is, I try to flag things like digital humanities because there are 4 people, I think, from King's College London's digital humanities group that are actually taking the course on YouTube, staggered. It's too early in London. So we will hit various topics in digital humanities in the course. So digital humanities is basically like history and sociology in the sort of information age. There's computational epidemiology. So if you're interested in actually looking at epidemic spreading on networks based on data that's provided by the World Health Organization, so huge graph data, basically. These are live data sets. You can sort of start thinking about it. And you want to think about it because I want you to be passionate about your project so that we can start steering the notebooks toward your interests, especially those who are enrolled. We can try to make sure that the topics are covered enough for you to get your hands dirty with the project. What else is here? Replicated data consistency explained through baseball, community sense and response. So this is, if there are anyone from civil engineering, then if you want to use your phone as a quake detector and do crowdsourced sensing and couple that with GeoNet, whether you correct it through Colorado's US Geological Service or not, you going to basically get tons of data for earthquakes. If you're interested in, in sort of taking that data and propagating that into damages, cost, and structures by PDEs, then the step before PDEs can be done in Apache Spark. If you're really stubborn, the step 4 PDEs can also be done in Apache Spark if you can actually do something called piped RDDs, which we could cover. So I'm personally, I already told you, I'm really interested in sort of state and non-state terrorist networks and what's happening in the state and national security, sort of social psychology, and counter recruitment, counter de-radicalization terrains. It's a very, very exciting area right now. So if you are interested in that, please come and chat with me. We have a bunch of sociologists who are interested in getting into problems like this. So there are some pointers here for this. This is very, very recent. It's from Current Affairs. You can watch the story on the rise of hate groups in the US. And if you're interested in understanding the emergence of hate groups in the online age and the science of it, you can work on projects. There's a nice Southern Poverty Law Center report that keeps track of various hate groups, and you could, later on we could build a bag of words model for sort of say I don't know, specific kinds of hate groups, like Black Power or Aryan Nation or whatever you want. Okay, so those things are of interest from a social psychological point of view. So there are people enrolled in the course explicitly for that reason, observing students. But of course, we're not going to do anything too applied here in the sense that we're not going to make software and sell it, right? It's just a project. Did you have a question? Okay, so here is other stuff. News aggregator apps. This is especially if you have some entrepreneurial angle and you want to understand how to maybe target news aggregation services to very specific niches. Then there's a lot of references here. Okay, there's an NLP. Sensing emotions is interesting if you're from the HIT lab or whatever, interested in machine detection of human emotion. There's a lot of links here. Okay, so yeah, and if you're interested in how to combine sort of supercomputing heavy, say PDEs for earthquakes in conjunction with fusing it with massive amounts of data, then you probably want to start with this Article 14 on how the two technologies actually are anticipated to come together. This is the high performance supercomputing technology and the big data Hadoop MapReduce like technology. Okay, so that's sort of I will be populating this. There should be at least 10 or 15 more projects, hopefully, that need to be scribed, but I think that's enough to get a lot of you started. Okay, so are there any questions about logistics? All right, so let's okay, so let's go back and continue from week 2. So I've changed week 1 material because I think I had way too much. So this is the current week 1 material. So you may want to just reclone week 1. Okay, because I've changed a bunch of links and slight changes to last week. Week 2 is basically this week. So you may want to go to Scalable Data Science, week 2, click here, and then hit clone. Okay, and once you hit clone, it'll tell you where to put it. You can put it in your home area. So I hope all of you have done this just very recently, because I was writing notes until very recently. Until literally 15 minutes ago, I was writing notes. So please clone and have a copy of week 2 in your area. Okay. And we will go through 004, which is first notebook in Spark Essentials. Okay, so is everyone here? Is anyone not in their own cloned copy of 004 RDD Transformations Actions notebook? Okay, good. So let's get started. So most of the lecture last week was conceptual, like ideas, and only toward the end we kind of got our hands dirty with some Scala code, right? Very basic Scala syntax. So you can sort of continue now with actual Spark essentials. All right. So in this notebook, I'll describe how to get started running Spark in Scala native code using this notebook. And our big accomplishments in this notebook will be how to create RDDs. RDDs are Spark's resilient distributed datasets. This is Spark's mechanism to ensure that there is a way to recover from false and dead worker machines, right? Which can happen with a high probability if you have a network of 1,000 machines. So then we will be performing basic transformations on RDDs and performing basic actions on RDDs. So let's look at the Spark cluster overview. Okay. So there is something called the driver program, which runs on your master. There is something called a cluster manager, which is a layer that manages the worker nodes, right? These are the worker nodes. And then there's the driver program basically connects to the cluster manager to allocate resources across applications. It acquires executors on cluster nodes. So executors are essentially processes that run certain computational tasks. They can cache data in memory. So there's a cache in each worker node where basically information is stored in random access memory or RAM, so very fast access. And that's basically what's happening in a worker node. The driver program sends application. What is application? Application is essentially a user program built on Spark. That's what we will be doing, writing applications here. It sends the application to the executors, right? These processes inside the worker nodes. And then the driver program sends tasks for the executors to run. Right? And what is a task? The computational task, it's a unit of work that will be sent to each executor. So you can look at the cluster overview.html and the latest Apache Spark documents to get a better overview of it. I've embedded this in place below, so for your convenience. So you can basically look at this in more detail later. Okay. And here's a nice glossary of all these swear words, right? Application, user program built on Spark, consists of a driver program and executors on the cluster. What's an executor? What's a task? What's a job? And okay. I have to look at that periodically myself because it's a lot to remember. All right, let's now get back into the abstraction, Spark's main abstraction of the resilient distributed data set. This is a software level abstraction. So RDD is fault tolerant. It's a fault tolerant collection of elements that can be operated on in parallel. That's essentially the definition of an RDD. Right. So there are two types of operations one can do with an RDD. One type of operations are called transformations. Another type are called actions. So I'm going to just play this video of Anthony Joseph's Berkeley course.
They are immutable once you create an RDD. You cannot change it. You can transform it. You can perform actions on it, but you cannot change an RDD once you construct it. Spark tracks lineage information to enable the efficient recomputation of any lost data if a machine should fail or crash. It also enables operations on collections of elements in parallel. Now you can construct RDDs by parallelizing existing Python collections, which is lists, or by transforming an existing RDD, or from files in HDFS or any other storage system. A programmer specifies the number of partitions for an RDD, and there's a default value that's used if you don't specify the number that you want to be used. Here we have an example of an RDD that's split into 5 partitions. The more partitions that you split an RDD into, the more opportunities you have for parallelism. So this RDD is split into 5, and those are placed onto 3 worker machines. Since there's only 3 worker machines, some of the worker machines have 2 partitions and one has 1 partition. There are 2 types of operations you can perform on an RDD: transformations and actions. Transformations are lazily evaluated. They're not computed immediately. A transformed RDD is executed only when an action runs on it. You can also persist or cache RDDs in memory or on disk. To work with RDDs, you first create an RDD from a data source, a file or a list. You then apply transformations to that RDD. So examples are map and filter. You then apply actions to that RDD. Examples are collect and count. So here we have a figure that shows, starting with a list, we parallelize that list. That creates an RDD. We then filter that RDD, creating a new filtered RDD. Then we do a map transformation that maps that RDD to a new mapped RDD. And finally, we perform a collect action, which now causes the parallelize, the filter, and the map transformations to actually be executed and return a result back to the driver machine.
Okay. So now let's just watch about transformations.
Smart transformations enable us to create new data sets from an existing one. Again, we're using lazy evaluations. That means that results are not computed right away. Instead, what happens is Spark remembers the set of transformations that are applied to a base data set. It can then optimize the required calculations and automatically recover from failures and slow workers. The way to think about this is we're creating a recipe for creating a result. So let's look at some examples of transformations. There's the map transformation, the filter, distinct, and flat map transformations. The map transformation returns a new distributed data set that's formed by passing each element of the source through a function. Filter returns a new data set that's formed by selecting those elements of the source on which the function returns true. And the distinct transformation returns a new data set that contains the distinct elements of the source data set. The flat map transformation is similar to map, but each item element, each input element can be mapped to 0 or more output elements. So this means that your function should return a sequence rather than a single item.
Okay. So those are transformations. That's the first type of things you can do with RDDs, and here are actions. And then after this, we'll play.
Spark actions cause Spark to execute the recipe to transform the source. Here's the mechanism for getting results out of Spark. Here are 4 Spark actions. The first action is reduce. Reduce aggregates a dataset's elements using a function. That function takes 2 arguments and returns 1. It has to be commutative and associative so that it can be computed correctly in parallel. The take action returns an array with the first n elements. And the collect action returns all of the elements of the RDD as an array. So you have to make sure that all of that data will fit in the driver program. Take order returns n elements ordered in ascending order or as specified by the optional key function.
Okay, great. So I just summarized the key points from the video. And what I've done here is put down the programming guide for you. This is essentially how most people start learning Spark. So the programming guide gets you through the essentials of Spark, so you can, look at more details here. And remember, if you go here, you have to right-click and come back here. So that's just there for you to get more details. Now, let's get our hands dirty in Spark, implementing these ideas, right? So before we do that, I want to share with you this visual RDD API that we are going to be using heavily. This was done by it was done by Jeff first, Jeff Thompson, And I think Steve Menyon might have actually found this, the original version in Python when we were taking the course. And this was essentially improved by Adam Brundle by Databricks. And we're going to essentially be embedding this material to make it easy. Okay. So we have to, first of all, understand a bit about the legend and overview of how to make sense of this visual RDD API. Okay. So it's a visual guide to transformations and actions on RDDs. It's not complete. I will populate these things as needed. And if you're wondering where it is, it's actually in Scalable Data Science Extra Resources Visual RDD API Guide. Okay. And various bits and bobs are here, actually. So I will sort of evolve them as we need, but what we need is here for now. Okay. So here's the legend for this visual API. An RDD is essentially shown by these blue rectangles. Each rectangle is an element of an RDD. And this RDD has two partitions, A and B. These two elements of the RDD are in partition A, and this element is in partition B. That's how we interpret this. And you later on see certain RDDs called key value RDDs or pair RDDs. For those RDDs, the legend will have a key in this black corner, and then the original value will be here. This orange rectangle is a transform type. So each element of the RDD, when it's transformed by a function through a map, then it'll be orange. And then this sort of dotted line with this black, it's actually a shell prompt. That's the driver, object in the driver, okay, driver program. So that's the legend. So user input comes in here. There's some user functions. Spark input goes here, and then this arrow is for emitted values. Right? You'll see more concrete examples. The dice actually represent randomized operations. We will see them in the sequel, not today. So you can do some scalable sampling and from the RDDs directly in these operators. And then this symbol stands for set theory or relational operators in like standard database language. And then this symbol is for numeric calculations. Okay, so sine, cosine, whatever, math operations. So Spark operations, as you saw, essentially are of two types, transformations and actions. Transformations are represented by the caterpillar becoming a butterfly, or transformation. And action is just the printer symbol. Okay, so that's the legend for what we need. And let me quickly show you what are all the essential core and intermediate Spark operations. So these are for transformations. Essentially, we have a bunch of general transformations. We'll play with them today: map, filter, flat map. And then the sort of math statistical ones are sample and red split, and set theory of relational ones are union, intersection, and so on. And the data structure IO ones are zip with index, key by, and pipe, and so on. Okay. So these blue ones are medium difficulty. So example, if you want to take all the earthquake data coming from sensors and want to plug in your PDE operators, then you need this pipe thing where you're basically passing the input to some C++ executables, perhaps. Okay. So this is the other type of Spark operations, actions. So we have reduce and collect. We will be doing today, we'll do take, and pretty much that's it, and count. So there are more complex ones called tree aggregate, tree reduce, and histogram, and so on. Okay. And of course, you can take actions like save as text file. So if you have something, you can save it to a text file. We'll see that down the road, not today. Okay. And here's more operations. Okay, so remember that the lineage graph is the recipe for creating an RDD. So this is in the paper. Did anyone read the Spark paper on RDDs? Okay, good. You didn't read it, Andre. Did you read the Spark paper, the original Spark paper where they introduce resilient distributed data sets?
Which is available online.
Yeah, it was in one of the links from last week. among all the links.
I read some, but I didn't know you could that.
Okay, it says bold read up before it. That's probably the only paper you maybe want to read if you want to understand, even at a high theoretical level, what's going on. So that's basically what tells you what a lineage graph is and how to recover from faults and so on. Okay. So now transformations can be either narrow or wide. Okay, so what does this mean? Narrow means each partition of the parent RDD is used by at most one partition of the child RDD. So we're transforming parent RDD into a child RDD. If you have this kind of a mapping where each partition of the parent is used by at most one partition of the child, then it's a narrow transformation, and it's represented by this symbol, a narrow bike lane. And then a wide transformation is when you have multiple child RDDs. See, all four of these child RDDs are depending on a single parent RDD, right? All these black lines go here, all these purple lines go here, and so on. So when you have stuff like this, it's actually a wide transformation, which means there's going to be a lot of data going through the slowest possible communication channel, which is essentially your Ethernet cables, okay? So you want to avoid that. So from the numerical point of view, a lot of the numerics is to try to minimize this third dimension of communication cost. So you want to essentially avoid the wide transformations. Okay, so here are some examples of narrow transformations. The ones we'll use today, map and filter, are actually narrow transformations. And I think we'll do group by key as well, and that's a wide transformation. And when you do that example, you'll see why it's wide. All right, so that's essentially our legend. So let's maybe leave that guy there. Okay, so the variable SC, okay, allows you to access a Spark context to run your job, right? Run your Spark program. So Spark context is in the driver program, you see from that picture. So you need the Spark context to actually start creating an RDD. And in the Databricks cluster, Spark context is made for you. The same way if you're running Spark shell on your own machine, SC is essentially available for you by default. In the more complex setting, you have to create the Spark context. Okay, so this is our plan for this worksheet. There's sort of 13 steps. The first one, we will create an RDD using sc.parallelize method. The second one, we will perform the collect action on the RDD and find the number of partitions it is made of using the get num partitions action. And the third, we'll perform the take action on the RDD. Then we'll transform the RDD by map to make another RDD. Then we'll filter to make another RDD. We'll perform the reduce action on the RDD, and then transform the RDD by flat map operation to make another RDD. Create a pair RDD. Okay, this is the key value pair RDD. Perform some transformations on pair RDDs, and then Siva is going to jump in and tell you about where in the cluster is your computation running for step 10. And then I'll just sort of go back to this more sophisticated notion of how Spark actually ships closures. These are your little functions that we saw in Scala last week. How does it ship closures to different worker nodes? What are broadcast variables and accumulator variables? And we'll revisit those notions again next week because they're fairly sophisticated, but just a brief overview. And then a summary of the Spark essentials. Okay. Of course, 13th is homework. You knock yourself out. There's a worksheet where a lot of these ideas and a few more actions and transformations will be cemented if you try them. Okay. So now let's create an RDD using sc.parallelize. So you just go in here and control enter. Right. So I've created a value, right? Val stands for immutable, name X here. So X has been assigned sc.parallelize. And what I've passed here is an array. This is just a Scala array of 1, 2, 3. Right? And then this comma 2 tells me, create my RDD with exactly 2 partitions in it. Okay, so that's essentially our first. Now, if X has been made, right, it says X is org Apache Spark RDD of type int. It's actually a parallel collection RDD. And if I go to X dot and hit the tab button, I will see, as we saw last time, all the methods that are available for that RDD we just made. There's a lot, okay? So these are various transformations and actions you can do with that RDD. So some of these were covered in the guide here I was talking about. So we'll do them slowly, one at a time, okay? So let's perform the collect action on the RDD and find the number of partitions that is made of using this get num partitions action, right? Because we haven't done anything. We just made the RDD. It's just kind of sitting there lazily, waiting to be acted upon. So now here's the collect action. Let's look at the collect action in detail. I won't do this for every transformation and action. But we'll do it for this one. So collect essentially returns all elements in the RDD to the driver program in a single list, okay? Which means you should be very careful about calling the collect action on an RDD made of 10 billion objects because the driver will crash, right? You just run the driver out of RAM. So here's my, but these are just tiny data sets so we can take the collect action. Here's the idea. You have an RDD made of 2 partitions, A and B, right? And then the collect action simply says the driver program will have a list of each of these elements in it. And it just prints it out. That's all collect really is doing. So if you want to, you can play around with the code right here. Then you have to clone it, which is another whole thing maybe you don't want to do. So what I'm going to basically do is go back here because I've put the code in place here at the bottom. So let's perform a collect action on the RDD. Of course, this is for Python syntax. This is for Scala syntax. I am told by the guys at Databricks that the new edX course at Berkeley will be trilingual. So it'll be Scala, Python, and maybe Java. Okay. So here is x.collect. We made x, so let's just control enter to evaluate that cell, and we just get that it's an array int, and the array itself is 1, 2, 3. So it's just coming back to the driver program as a list and just seeing it printed here. Okay, so I already cautioned you about calling collect on very large collections because it'll crash the driver. There's a bug. Sorry about that. Okay, so let's look at the get num partitions action in detail. This tells us how many partitions the RDD is made of. That's all it does, right? So this partition, there are 2 partitions, A and B, so the answer will be 2 if you call get num partitions on. Right? So that's exactly what I've done here. Control enter, and I get 2 because I specified it to be exactly 2. So I guess you guys have attached this to another cluster, right? So if I can maybe detach, and I'm going to reattach to, say, enroll students cluster. So it's the same protocol last time. Those who are enrolled students, please attach to this cluster, and the observing students to the other observing students cluster. Okay. So now, of course, this is a new cluster, right? So I have to go back and reevaluate this. Okay. So now X should be there, and if I do x.collect, I should see that. And again, this should be 2 because I've just specified 2 partitions. So now what's nice about glom? Glom is a nice way to know what is in which partition, right? So if I do x.glom, it flattens elements on the same partition, then I can do .collect on it, okay? So this will now tell me that one partition has element 1 and the other partition has elements 2 and 3. Okay, so it's a nice way to kind of take a closer look at what's in which partition. And of course, you need to do that if you want to minimize communication costs and so on. Okay, so here's a you try. So you try means you try. So please put your sort of cursor here, and you can shift enter and move to the next cell. So if you notice, we're doing something different now. We're not specifying a comma 2 anymore, right? Show result, sorry. Yeah. Yeah, so I don't know, I might have hidden the results. So do show result maybe. Yeah. So now what we've done is we haven't done this comma 2, right? We're not saying make an RDD with 2 partitions. So I have no idea what the number of partitions under the hood is. It's the default value, right? So now let's shift enter and find out it's 8, right? So why did it put 8 partitions by default? So, and then let's glom and collect and see there's a lot of partitions with nothing in it. There's one partition here with 1 and another partition with 2 and another with 3. The rest are empty. Right? So if you want to understand why that's the case, you can chase it in the programming guide, right? It's a complicated function. Well, in this case, it might be simple. It's the number of worker nodes, I believe, right?
The number of cores, total number of cores from all the worker nodes put together.
Yeah, total number of cores from all the worker nodes put together. So yeah, and it gets more complex if you construct RDDs or transform RDDs based on pre-existing ones and things like this. So the programming guide gives you pointers to it. Okay, so often you may want to put 200 because you want to use the 8 default partitions would be too low for you. So you can maybe put 300 or whatever, because the more partitions you have, the more parallelization you get. But it's again at the expense of maximizing communication. So it's so I think after next week we are going to sort of direct you away from the RDD land to the land where things are done for you, which is basically data frames, a little bit of data sets, and Spark SQL, right? So these things are essentially another layer on top where you just do more abstract operations, and the Spark developers have taken care of how to do the logical plan and the physical plan to lay out exactly how your operation should be carried out on the machine to minimize communication cost and whatever. So it's a big art, okay? So we're going to quickly take you to the la-la land because you don't want to be messing around here, right? You really need to know what you're doing to do work directly with RDDs. Of course, you can come back and...
if you've got, like, say, 8 cores, and if you partition your RDD into 300 partitions, that's just going to mean a lot of context switching or something. The threads on the workers are going to be a lot of context switching between the cores. That's what it means.
Yes, that will happen. But what it will also mean is each of your partitions has lesser number of work to do. Like the amount of work it has to do is less. So let's say when your program is running and one of the worker crashes, and the recomputation that it has to do will be much lesser.
Yeah, but if you have like a massive number of partitions, then you might lose the benefit because there's a lot of context.
Yeah, absolutely. So you don't want a million partitions. So there's definitely, it's going to be heavily dependent on your particular sequence of transformations and actions. In fact, there is a whole thing in AmpCamp 6 where they're actually doing regressions on director acyclic graphical expressions of what you want to do to optimize the layout. That's
just unclear. Does it mean that a partition takes exactly 1 thread to execute? Occupies 1 core or 1 thread, or it's independent?
Yes. It's one code.
So and they all run in parallel, so they don't wait each other.
Yeah, they all run in parallel.
Yeah.
So a worker is a JVM, and an executor is what, a thread or something, a thread pool.
So when you submit a job, the driver will contact the worker, and the worker will spawn an executor for you, and your actual computation will take place on the executor.
The executor is a thread within.
It's actually a JVM itself, and during the entire process of running your job, that JVM will be alive.
The worker is like a manager of multiple JVMs. So
Yes. Yeah.
Yeah, so next time you talk, you should maybe come here because the guys can turn on. Okay, so let's, it's good. It's good that a lot of engineers here. A lot of it is abstract for me, to be honest, right? So, yeah. Let's continue. Right, because I was attached earlier to a different cluster and I noticed that the number of partitions is 2. And then I read the thing I told you guys should read. So I put it here. So when I switch between clusters, the default changed. Okay, that's just getting the number of partitions and calling collect. Those are very basic actions we like to have. Now, collect, I said, is dangerous because if you call collect on something huge, which we typically will be working with, it'll crash your driver. So a nicer thing is called take. So take 2 just returns the first 2 elements of your RDD.
What actually happens in Databricks if you crash your driver?
I don't know. I haven't. I think it just restarts the cluster, or maybe Steve knows what happens. I don't know. I usually haven't crashed it yet, so I don't know.
Yeah, no, it just does fix it, but sometimes weirdness. Like, yeah, big libraries and then crashes and then this does not fix. But if you don't manually set it's fine.
Yeah, so Dylan has had a lot of crash testing of Databricks because he's doing some summer internship. And so he says you have to manually restart it sometimes because it may not have a Spark context. But all right, so let's continue. So here's a utry, and please fill the number in this parentheses to just take one element from the RDD X, just to make sure you're doing something. So I'm asking you to just take the first element, not just 2, right? So that's okay. Oh, this is my bad. I'm sorry. So you have to show result because I kind of hit these results. Okay. So I don't know. I've never tried 0. I wonder what will happen. Oh, interesting. Okay. All right. Has everyone taken one element? Yeah. If you're stuck with something, please raise your hand so maybe Siva can field you. Okay, so the next transformation, probably one of the most important ones, is map. Okay, so this is the map from MapReduce, right? So we will transform the RDD by map to make another RDD. And let's look at the map transformation in detail visually. Okay. So what does map do? Map returns a new RDD by applying a function to each element of this RDD. So here's a RDD X with 3 items in it. Okay, I'm not showing the partitions. And then we're going to apply a user function item by item. So it's first applied to this item, get the orange one, and this item, get the next orange one, and the last item. So that's basically map. So it's a narrow transformation because it's going one element at a time, right? So it's so after map has been applied, you get this before RDD and after RDD. That's kind of the idea, right? So here's the idea together with the code bits for Python and Scala. So instead of doing it here, let's just go back and continue with here. So you don't have to clone it. Okay, so here's X, and let's do sc.parallelize array B, A, and C. So it's just an array of 3 strings, B, A, and C. We're passing it into sc.parallelize to get an RDD X, right? So now we're going to create another RDD Y, which is going to just x.map. And here's your closure, right? Z is becoming Z, 1. So we're mapping each value in the RDD X to a tuple, right? Value, comma, the integer 1. So let's shift enter. And now it's saying X is a arg Apache RDD string, which it is, and Y is a string, comma, int tuple. Right? This is a parallel collection RDD. This is a map partitions RDD. Right? So map partitions is actually the low-level function that's being called. All right, now I'm just using Scala's print line, and I'm simply collecting it and printing it separated by a comma with the make string operation. Right? So let me control enter, and what I'm going to just see is B, A, and C, and B1, A1, and C1. That's all I've done. Just mapped each element to a ordered pair, to tuple. Now let's transform the RDD by a filter to make another RDD. So here's filter transformation. I'll probably go a little bit faster on this time. So filter is basically going to take your RDD with, say, 3 items. It'll apply a user-defined function and see if it emits a true value or not. If it emits true, it'll keep it in Y. In this case, it emitted false, so it doesn't keep it. And so here's basically only the first and the second element pass the test, the function. It's a predicate, which returns true. And then we basically have before RDD and after RDD, after the filter is applied, and that's a code bit. So we can again do it here, val x equals sc.parallelize array 1, 2, 3. And then what we're doing is x.filter, and here's our closure. So we're taking n, which is now an element of the RDDX, and the function is basically m%2 equal 1. And all this means is what is the, is the remainder of n when divided by 2 equal to 1? If that is true, then it'll pass the test, okay? So that's basically what we're doing here. Okay, and now we have, again, another map partitions RDD from the parallel collections RDD, and I'm simply going to control enter and evaluate that. Okay, so we, of course, 2 divided by 2, remainder is 0, it's not 1, so we've lost 2. Okay, now let's perform the reduce action on the RDD. So here's again reduce action in detail. So what we're going to do is reduce basically aggregates all the elements of the RDD by applying a user function pairwise to elements and partial results, and it returns a result to the driver. Right? So this is actually an action. This is like how we added in Scala last week, but now we're not doing it in Scala. We're taking the Scala vector sc.parallelizing it into an RDD and then doing reduce on the RDD. Okay, so that's because now we can just scale it to a huge number of a vector that's very, very long. Okay, so here is my 1 plus 2. This is addition example for this reduce. It emits 3, and then 3 gets added to this 3, and it becomes 6, and 6 gets added to this 4 and becomes 10, and then it returns to the driver program as 10. So 1 plus 2 plus 3 plus 4, done pairwise, is 10. And the beauty is the order in which the operations are done don't matter, because addition is commutative and associative. It's all good. Okay, so that's basically reduce. And here is basically our code bit for it. We're just going to parallelize and do reduce. If you look at the closure for the reduce, we are taking an ordered pair A comma B and then transforming it with this A plus B, right? So we're reducing it with the addition operator. So I'm going to use this kind of explicit Scala syntax instead of the underscore syntax as much as possible to be clear, and especially in an industrial environment, you want to understand each other's code. So this is a lot easier. Okay, so now that answer is 10. So y is now a pure integer, right? 10. And I'm simply printing stuff. Now, let's transform our RDD by using flat map. Take another RDD. So what is flat map? This is another bread and butter type transformation. So flat map returns a new RDD by first applying a function to each element of this RDD and then flattening the results, right? So visually, this is what's going on. So you have an RDD X with 3 items, and let's say X gets split. It could be a long sentence. That's what we'll be doing toward the end of this lab. It'll be a long sentence with spaces in between. So you could take that string, which is a sentence in the State of the Union address, split it by spaces. So then you're going to get a lot of words as strings. So what do you do with these words, right? So you want to flat map it. And this is essentially how you would do it. So you would take, each element of the RDD could be a line in the text with the end of line character. And then we just break it by white spaces and then spill the words here. That's essentially, you can do it line by line with flat map operator transformation. Okay, so that's what happens. Before we had an RDD of sort of 3 lines, and then after you have an RDD of a bunch of words from each line. So that's basically flat map. So let's do again flat map in a nice little example for us. So here is sc.path. We have an array 1, 2, 3, and I'm flat mapping the array so that I take each element of the array and transform it to another array, right? Each element becomes an array of n, which is the original value, n times 100, so the original I multiply 100, and just the constant 42, right? So if I do this, I have my parallel collections RDD and my map partitions RDD, and then I control enter, and I'm printing what's there, and you'll see that I took the RDD 1, 2, 3, and then 1 became 142, 2 became 2, 242, and 3 became 3, 342. Right? So that's flat map. Okay, so let's next create a pair RDD. So this is essentially key value pairs RDD. This is a very fundamental type of RDD. So here we're going to create a val called words, and words is going to be taking this array of strings, made up of letters A and B. I have A, B, A, B, B, A, B, 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 B. So that wasn't planned, BB. So words.collect is here, right? So I'm going to control enter. So I'm basically seeing I've made an RDD called words, and I've collected it to display it as an array. Now what we're going to do is make a pair RDD called word count pair RDD. Okay, so you can call it whatever you want. So the key is here. I'm going to take each word in the, say, S, each string in the words RDD, and then map it to S, 1 and collect to show you what's there. We've done this before. So now A gets coupled with 1, B with 1, and so on. So we're essentially counting the occurrence of each word. Okay. So now what do we do with these paired RDDs? We want to do some transformations on these paired RDDs next. And the 3 types of transformations, we're going to, 3 transformations we will do are reduce by key, sort by key, and group by key. Okay. So what does reduce by key do? It just takes an RDD and returns a new RDD of key value pairs such that the values for each key are aggregated using the given reduce function, right? So it's just like before when we did just dot reduce. Now we're just going to make sure we reduce only the values that belong to the same key. Okay. And then sort by key essentially sorts the pair RDD by key in ascending order. So the key is alpha is our strings, and it'll be lexicographic. And then group by key is another transformation that see pictorially here. Here's reduce by key. Let's add A1, B1, and what is reduce by key doing? It's basically, in this case, A and B are different keys, so it's going to leave them alone. In this case, there are two A's and two B's, so it'll actually reduce these two because they have the same key, so it gets A2, two A's and two B's, B2. And here it'll be A3 and B2 because there are two B's and three A's, right? So it's just doing this now nicely in each partition, and then it'll do further reduce by key and continue like this. So in this case, it'll actually join these two A's and get A6. All three A's and all three B's and so on. So this is our final result, right? It's reduced by key. So let's control enter here. And what we have is A6 and B5, just done reduced by key. And here I've used my sort of naughty underscore thing because I sometimes get lazy, right? So if you want to do this properly, you can, right? You just have to basically put V1 comma V2 in parentheses equal. So let's do that. Control C. Yeah, so I'll comment this bit out. Value 1 comma value 2. And I won't be surprised if this doesn't work because I have no idea. Okay, so it should work, I think. So let's see. Control enter. Okay. So this is much better syntax for people to read. This is a little too. Okay, so now let's do all of them together, right? So this is something we will often do. So I've done words dot map, and then I've done dot reduce by key dot collect. Okay, all at once. So this is something we will be doing a lot, right? So you want to be able to understand what's going on in a whole sequence of transformations until the last action is done, right? So here's the sort of last action. So here's a you try. So please try. I hope I haven't hidden the. Yeah. So try to see. What I'm showing you here is sort by key. I'm not walking you through sort by key. I think you can kind of walk yourself through sort by key. So please go ahead and try. You will be having to do this for all those other transformations and actions I won't have time to cover, right? So you can go through the programming guide and the Scala docs and try to understand them. So if I shift enter this, I'm going to realize that I've made an RDD of words, an RDD of word count pair RDD, and a word count pair RDD sorted by key. Now, I haven't done any actions. These are all just RDDs and transformations, creations and transformations. So they're all lazy. So now I'm going to collect and actually take an action. So, and then it gives me A1, B1, A1, 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 B1. This is my word count pair RDD, which is mapping it to the ones. Now here's my word count pair RDD sorted by key. Once again, just should probably say control enter here. Okay. So now you see it's arranged it by lexicographic ordering of keys. All the A's are in the front and all the B's are in the back. So that's very helpful, as you'll see very soon. Okay, so here is the group by key. I wanted to bring group by key because this is an example of a narrow white transformation that can go really wrong. if you don't know what you're doing. So what happens, and let's look at a picture, what's going on in group by key. So in group by key, essentially, the elements are going to get aggregated together first, right? So here is A1, B1, and here's A1, A1, B1, B1, and so on. So when we basically, what we're going to get is get all the A's together and all the B's together, okay? So this is essentially how group by key works. So we end up with a new RDD that contains just 2 elements, and the first element is going to be B, and it'll have an iterable compact buffer, which is just an iterable that keeps track of all the values that are associated with the first key, right? B. So this will be just 1, 1, 1, 1, 1. So it actually just groups all the values into one big thing. It's not like reduce by key, right? Because I'm not adding pairwise, I'm just aggregating, grouping. So that can really increase your communication cost if you don't, yeah. That's not what you really want, right? So let's shift enter here and collect it. And that's what I've seen. So it's an array, and I collect this A, and it's just a Scala iterable compact buffer.
You may consider to improve the picture because it does not reflect the reality.
What does not reflect the
The
reality?
picture above,
Oh, right.
this on the 2 boxes in the bottom, that's not what we see in the result.
Yeah, this is, I think this picture is coming from here. I haven't, they haven't made an atomic breakdown of group by key, and if you could contribute directly to GitHub, everyone would love it, because then you can actually, I know what you mean, right? Yeah, yeah, no, you're right. It's just contrasting it to group by key. There's only one image, and I'm sort of, yeah, it'll be good. And the idea is that more people can contribute, and the visual APIs can be, yeah. Yeah, I think this yellow thing is, so if you really want to atomically split this, actually, this yellow thing is coming from this yellow thing, and they're just saying it's different from this one. All right, so we won't be using group by key much in this course, right? It's just something to be aware of, and as I said, we'll quickly take you to a nicer land where all these low-level things are done for you. But you have to know a little bit about what's going on. So now Siva is going to come and show you something about where in the cluster is your computation running.
Okay, so the reason we need to know where in the cluster the computation is running is because we want to debug our programs. More often than not, we end up spending a lot of time debugging programs. So it's good to know where our code is getting executed. So the first block of code you have here is simple Scala code. Don't worry about the notation. This 1 to 10, it's just creating a range of values which range from 1 to 10. And then we have a variable called sum. And for each of the values in the list, we are updating the variable sum here and then printing it. This is normal Scala code, and it will run as you expect it to. And the same thing actually done in Spark. We are creating an RDD with 10 elements, right? The same 10 elements actually. And it's the same variable sum. I mean, just the name is the same, but, and we're updating it in RDD land. And can anybody guess what is the expected outcome?
Bug.
No.
So sum won't be the result.
Yeah, okay. It's not displaying because I had hidden the result, but okay. So the explanation, sorry? Yeah, it's 0. The reason is because here in this case, remember that for each or map, all of these transformations are lazily evaluated. So actually nothing is computed. So that is why sum is still 0. So this statement is actually not executed on the cluster, right? So it's just printing the sum here, right? Now if I change it and if I put in an action, okay, so let me call, say, collect. Okay. So it's collecting it, but it is still 0.
Wait, for each is an action, no?
For each is a transformation. Still a transformation, yeah. So it's still 0, and the reason here is because you see the variable sum is actually defined on the driver. So only the code that is in this closure, right, for each closure, only that is actually shipped and executed on the executor, right? And on the executor, the variable sum is not defined. So what Spark does is it looks at this variable and looks at the scope of this variable. So it's available on top here. What it does is it sends, instead of sending just this bit of code to the executor, it sends this whole code to the executor, right? And it also sends the value of this variable sum to the executor. So on each local executor, if we have 10 partitions, for instance, some will have 10 copies, all of them will be 0. On each executor, some will get updated, this line of code. And then you don't return anything because it's just a for each. So the sum that is printed here is actually the value on the driver itself. So it's still 0. Okay. So this is different from how we write our regular program. So we have to be cluster aware when we write our programs. So to overcome this, Spark has provided some other abstractions like accumulators. And I think the next video is about accumulators. Thanks.
Okay, so there will be more stuff. So let's just watch this video. Okay. So this is about shipping closures, broadcast variables, and accumulator variables. This is again AJ or Anthony Joseph's.
Spark automatically creates closures for functions that run on RDDs at workers and for any global variables that are used by those workers. Now, one closure per worker is sent with every task, and there's no communication between workers. And any changes that you make to the global variables that are at the workers are not sent to the driver or to other workers. Now, consider the following use cases. What if we have an iterative or a single job that has a large global variable? So this would result in sending a large read-only lookup table to the workers, or sending a large feature vector and a machine learning algorithm to the workers. But what if we want to count events that occur during job execution? So for example, how many input lines were blank, or how many input records were corrupt? The problem we have is that these closures that are automatically created are sent or resent with every job. So for an iterative job with a large global variable, we'll be sending that large global variable with every single job to every single worker. It's also very inefficient to continually send large amounts of data to each worker. And closures are one way from the driver to the worker. So how can we count events that occur at a worker and communicate that back to the driver? To do this, PySpark provides shared variables in 2 different types. The first is broadcast variables. These enable us to efficiently send large read-only values to all of the workers. They're saved at the workers for use in one or more Spark operations. And it's like sending a large read-only lookup table to all of the nodes. The second shared variable type is accumulators, and they allow us to aggregate values from workers back to the driver. Now, only the driver can access the value of an accumulator. For the tasks, the accumulators are basically write-only. And we can use this as an example to count errors that are seen in an RDD across workers.
Okay. So I think we will play around with at least broadcast variables maybe next week. Again, this is a low-level thing we will try to get away from as soon as we can. So there's a summary of broadcast variables and accumulator variables. Here's a very, very final, very brief summary of the whole work notebook.
So in summary, when you write a Spark program, use the master parameter to specify the number of workers. When you create an RDD, you can specify the number of partitions for that RDD, and Spark will automatically create that RDD spread across the workers. When you perform transformations and actions that use functions, Spark will automatically push a closure continuing that function to the worker so that it can run at the workers.
Okay, so we are creating the number of workers for you when we create the cluster, because only some of us have admin rights to create cluster. So that part, you don't have any control. The other thing I should point out is you saw in the video PySpark, that's basically Python API for Spark. There's also Spark R, which is the R API for Spark. Of course, the video is done in Python because more people in the world are into Python. So sometimes you know, these videos are quite good, but it's really about Spark, the parts I'm showing here. Okay, so please knock yourself out with homework, right? There are some new actions, take ordered and transformations called distinct there. I'll just briefly point out there are, for those who are trying to sort of make money using numerics in the industry, there are some very elementary lessons on numeric types in Scala and when things crash, knowing numerical bounds and things like that. So just play around with this, sort of, because you can quickly create a seek.range is a method that will just create a bunch of integers from 0 to 1 million or whatever. And I'm sort of showing you some of the limits of the built-in Scala types for integers and you know, and so if you do reduce operations that involve multiplications, you know, you can leave the numeric range, right? You have to be aware of things like this. So you'll probably learn a few things about numerics and what happens when you want to do reduce operations. Okay. So of course it's not graded. I am monitoring what everyone is doing, of course, very nicely. So, but there's no grade for, you know, the enrolled students. Okay, so this is our word count example. This is the State of the Union addresses. And I think we can kind of go through this in 15 minutes and then people can kind of go home. If you take a break, maybe, unless someone really has to run to the toilet or whatever, we're happy to wait. Probably nobody's going to do this now, right? You know, we can take a 5-minute break now, or I can continue and finish this by 6. What do you guys want to do? Okay, sounds good. So here's the word count on the US State of the Union addresses. And I told you a little bit about it last week. This is an interesting analysis of textual content of the State of the Union addresses by all US presidents. It's there's this nice PNAS paper one could kind of look at. I'm going to actually spend just a tiny bit of time, have that load, because if anyone is interested in sort of digital humanities or like meaning extraction from English strings, like some kind of natural language processing, especially in a historical context, and possibly recreate the results in this PNAS paper, and in fact, it's not going to be too hard to do something slightly different, then you know, I've already done the ETL for you here, right? So it's a nice project, actually. So what this paper talks about, it has a lot of figures. I really like this one. This figure 5 from the PNAS paper is talking about a river network that's trying to capture the flow of sort of concepts across history in the sort of US political discourse. And you know, these are sort of political scientists that are writing this. Time moves along the x-axis. Clusters on semantic networks of 300 most frequent terms for each of the 10 historical periods. So they have period 1 here, period 2 here, and so on. There are 10 periods, broken up US history into 10 periods. And they're looking at clusters on semantic networks of the 300 most frequent terms for each of these. And then the relationship between clusters of adjacent periods are indexed by gray flows, and the densities are reflected by the degree of connectedness and gray level. And streams that connect at any point in history may be considered to be part of the same system, and so on. So, you know, you can see in the beginning, you know, and engineers, of course, Second Amendment, arms and service, and land and limits, and things change a lot, right? So in the U.S. political discourses, World War I or II is here, I think, somewhere here. So, okay, so it's definitely a very interesting article to read. Okay, so we're going to investigate this data set ourselves. So first of all, we want to get the source text by scraping and parsing it from this particular URL. So if you go here, so here is stateoftheunion.123.net. I have no idea. It's the first thing up in Google search. So they have these things. So as you can see, these are nicely labeled by the year, day, month, and date of the address. So the first several were by George Washington, and then John Adams, and so on. And the last two should be by Barack Obama. Oh, the last several, yeah, 2 terms. Okay, so that's essentially, but then if you go and click one of these things, what you're going to get is the actual sort of plain text embedded in HTML. So you have to somehow parse this. So so this is not, and you don't want to do this mechanically. So this is what's done here. So Paul Browers did this. So this is, again, a worksheet that's here. I'm going to sort of put them in extra resources, SDS datasets. I already negotiated with people at King's College London and the Old Bailey online team. So we will also have the English court records from this court called London's Old Bailey. Every single court record from 16-something to 1910, right? So there's a huge resource. We will have that here as well. So here's the scraper for the State of the Union address, and the ETL extract, transform, load, piping. And if you're interested, it's basically just one line of bash, right? And links is essentially a text-based browser, and then you're just grepping it, and there's a lot going on, right? The sed is a stream editor, and then you're tailing it and cutting stuff off and heading it and cutting some stuff off and resetting it and setting it. And, okay, it's a lot. I don't pretend to understand this, right? But it works. So here's the thing, it's broken down line by line if you really want to. And it's there because we may have to use this again later on. And if Paul is busy or whatever, we can figure out how to do it. Yeah.
Who's Paul?
Paul Browers is a research programmer or system administrator in the School of Mathematics and Statistics, IT support team. Yeah. So officially Paul Browers and there's another guy named Dylan George. They're assisting the course. All right. So that's okay. That's there. So it's not sort of black box and not. So now what I've done at the end of that worksheet, I've basically taken that data and loaded it into the distributed file system. This is actually an important step. So for those of you who want to play around, so once the data was parsed, what I've already done is put the data in actually my home area, right? So if you can do in %sh is bash shell, you can wget this tarball. Okay, so you can just get that, and I've simply downloaded it from just my home area and then just extracted it. And once I've extracted it, whatever, checking environmental variables, looking at what directory I'm currently in, and then making sure the files are okay. So I just do some basic checks using bash. Just remember, we can call bash from here. This is the first 5 lines of this file. Just making sure that he's the last. And then I do display ddutils, so we'll learn more about it, find out where the file system is. And then I made a directory called SOU here, State of Union, and then just essentially loading the data into that directory by this copy command. So I'm sort of, once I've done that, now I have those text files in the distributed file system that I can read. That's where we're going to jump to next, okay? So it's not like magic. It's something you will have to do later on for your project. So I'm just showing you the steps that are here. Okay. So let's make sure everyone is on the same page here about key data management concepts.
So in review, the big picture is we have a data warehouse. And from that data warehouse, we'd like to extract data products, analytics, and business intelligence. We get information into the data warehouse by performing extract, transform, and load operations on application databases, files, and logs. Now, some of the key data management concepts that we want to consider are a data model. This is a collection of concepts for describing data, and a schema, which is a description of a particular collection of data using a given data model. Now, information spans a structure spectrum, ranging from unstructured or schema-never data. This is information that has no structure and never will have structure. It includes things like plains and meaning. Semi-structured or structure-later data includes things like documents, extensible markup language content, and tagged text or media. The last structure element is structured data, and this is schema-first data. This includes things like relational databases and formatted messages.
Okay, so we're in this unstructured land for this example. It's just plain text. Okay, so I'm going to let you watch this later. It's just something about files. If you don't know how files are structured in a file system, please look at it later. So what we want to use is essentially DBFS, or distributed file systems, and DB utilities. Right? Because we are in the Databricks cloud, we're going to basically use the distributed file system, which is very similar to the Hadoop distributed file system. It allows us to interact with it, the DB utils, and the display command tells us basically where these, the stuff that I showed you how I loaded into this DBFS. So this directory SOU that I created essentially has all these files. So starting from the earliest one, 1790, all the way to 2016. Okay, so all the files are here, and this is the name and the size and so on. Okay, so the next command shows you how to read the first 673 bytes of the file. I don't know, I'll tell you why there's 673. I sort of did this by trial and error. 673 corresponds to the first 5 lines of the file. Okay, that's basically that. So you can kind of peek and look into the first several bytes of the file. And you want to look at the first several bytes, not the first several lines, because the notion of the line break may not exist for every file. So here's a utry. So please try, modify the XXXX below to read the first 1,000 bytes of the file. Okay. So now you can sort of, the first 1,000 bytes are here. As you can see, it's sort of stopping midway, right? So it's the first 1,000 bytes. So I'm going to comment this. And it's kind of, okay. Now let's read the file into Spark context as an RDD of strings. Right, so here's my, my Spark context. Let me do this. So I'm using a new command called sc.textfile, right? That's it. To read a text file, you just use sc.textfile. And what it's going to do is basically load it up for you. And what you're getting is a RDD of strings. And it's going to have each line as an element in this RDD, each line of the file. That's what the default behavior is. Okay. So now let's perform some actions on it. Let's go and count. This is an action we haven't seen before, I guess. So count simply counts the number of elements in that RDD. So there are 23 lines in the way we parsed it out of that web page in the first State of the Union address. Okay. These are not 23 sentences. These are sort of 23 things demarcated by end-of-line characters. Okay, so now let me take the first 5, right? And I can see the first line is George Washington, and then there's an empty line, and then the date, fellow citizens of the Senate and House of Representatives, blah, 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 right? So now I'm going to, this kind of display is a bit hard to parse because it's just showing an array. So I can just do take 5 and then do dot for each println. So this will just give me a much nicer, something that the web page shows me, right? So who spoke when, this is exactly the first 5 lines. And then of course I can do dot collect and see the entire contents of that RDD, the first SOU, State of the Union, right? So here's the full thing, and you can just browse, oops, you can just browse. Strange. I don't know why I can't browse. Strange, sorry. We should be able to, can people go in here and move down the cursor? All right, I don't know what's going on with mine. Okay, so yeah, you can see the whole thing. So then cache the RDD in distributed memory to avoid recreating it for each action. This is another important concept, okay? So if you just take a whole bunch of actions and transformations again and again, it's going to start from the original RDD, from the distributed text files, and do the whole thing again and again, right? So the whole point of Apache Spark, remember, compared to Hadoop MapReduce, is that we can use distributed RAM, right? Distributed cache across all the nodes. So we can just call the .cache method and then have the RDD cached in distributed RAM memory across all the nodes, and then we're going to be doing things a lot faster. So anytime you want to repeat it, this is a good idea. Also be careful because you may not be able to store things in distributed RAM unless you have enough nodes. That's a different problem. Okay, so here is what I've done is now just do sc.text file, and then now I'm just saying just .cache, cache the RDD in memory, right? So let's just shift enter and evaluate this. Now I'm doing a count. Okay, so now let's see how long this takes. This took 0.42 seconds. Okay, only when I did the dot count did my RDD get called. Okay, because up to the dot cache it was all lazy, but the first dot count method made it actually construct, and then it cached it. Now if I call this dot count again, it should be a lot faster. It's only 0.07 seconds instead of 0.42 seconds because it's not reloading it all the way from the file system. Okay. So that's a nice thing. And that's exactly what we will be exploiting for machine learning pipelines down the SQL, because we want to have iterative operations done on machine learning pipelines, because we will be manipulating objects that we've created with a lot of hard work, putting it in cache, and then continuing to iterate on them. Okay. So this is a very important idea. So now, once again, you see when I do take 5, it's again super fast. I can just get it in 0.06 seconds because it's already cached. Here's a life cycle of a Spark program in 23 seconds. Okay, so that kind of summarizes a lot.
The life cycle of a Spark program is that you first create RDDs from some external data source or parallelize a collection from your driver program. You then lazily transform these RDDs into new RDDs. You cache some of those RDDs for future reuse, and you perform actions to execute parallel computation and to produce results.
So easy peasy, lemon squeezy, right? So that's basically it, right? Here we're going to just do slightly more interesting things. So let's transform the lines into words, right? What I've done is I've taken the RDD, the first State of the Union. I've done .flat map. I've taken the line and then split the line by white space characters, and then I'm taking the first 100 of them to show, right? So remember, flat map will take a whole line and break it up into white space characters and turn them into an array, and they'll all sort of work together, right? That's what I've done. So now I have George Washington separate, and then there's this empty string and so on, right? That's the empty line we saw, and so on and so forth. So the problem is this has some issues, right? This way of directly breaking it by white space has issues because there's a lot of formatting we need to be worried about. So what we want to do is a naive word count first. So for the naive word count, we will just use the closure where we map each word to word comma 1, the tuple, and then we will just do reduce by key on the key value pair to count, right? To count the number of words of a certain specific word, number of occurrences of a specific word. Then we'll collect a display. That's what I'm doing here. Dot flat map line dot split, which is what this is. Now I'm going to do a dot map where I take each word, map it to a tuple, word comma 1, and then I do reduce by key, and then I do dot collect, right? So let's just try that. And it's done it. So call has been said once, country 3 times, house 3 times, promoted 1 time. This is the beginning of natural language processing, right? This is the beginning step for latent Dirichlet allocation and topic modeling and so on and so forth. So we will come back to more interesting applications of extra steps from here, right? So now, unfortunately, as you can see, what's happening is there's a lot of punctuations, and there's strange things happening, right? We have like licentiousness dash, right? So we want to somehow do a slightly better job of this. We want to remove punctuations, and there's when there are 2 consecutive white spaces, it'll break it into 1 white space, and the other white space will be turned into empty string and things like that, right? So we want to make it slightly more robust. For that, what we really need is regex, or regular expressions, right? So regular expressions allow us to essentially deal with this. So in this example, I've just sort of made an example string called val example, and this is basically, my head sometimes, right? This is master, it's me, Smeagol. But they took away our precious, they wronged us. Gollum will protect us. Master, it's me, Smeagol. So anyway, so this is something I do a lot, right? If you have little 10-year-olds, So that's kind of my string, and I'm going to now just demonstrate a little example where I do dot replace all. This is just a Scala method. And I'm basically replacing multiple white space characters, including space, tab, new line, etc., with this / s plus, okay, with 1 white space character. That's what I'm doing, kind of globalizing the white spaceness. And then I'm doing a dot replace. This little, so the outer parentheses basically is saying here's the pattern, and the inner parentheses, the brackets, are specifying exactly what characters are I want to be replaced with nothing. So these are all the punctuations I want to get rid of, right? Comma, question mark, dot, exclamation, colon, semicolon. And then finally, I want everything to be in lowercase, right? So that's all I'm doing here. And if I do that, I basically will get master, it's me, Smeagol, blah, blah, so I haven't replaced the star or the percent sign because that's not included in my list of punctuations to exclude. So this gives you enough Lego regex to play around with other examples you may want to do. So now here's a more sophisticated word count. We're going to take the same file. We're going to flat map it. We're going to take a line and then take the line and do a replace all, where we're going to do essentially exactly what we did. Replace all to get 1 white space, remove the punctuations, turn it to lowercase, and then split by 1 white space, right? And then we're going to map each word to the the tuple x comma 1, okay? And I'm going to reduce by key, right? So this is a more sophisticated word count, which will be slightly more meaningful. So now I know university is 1, call is 1, country is 4, promoted is 1, and post roads and whatever, well digested, and licentiousness dash is that because I didn't remove the dash, right? So you may want to. So we'll do these things nicely next time with broadcast variables and more sophisticated things. Okay, so finally here's my top 10. So there's that sort by method, which is in your homework. It'll tell you how to do a sort by so when I do underscore dot underscore 2, it's sort by the second element in the tuple, which is the count, the word. So it'll sort by the most, the word that occurred the most, right? So that's what this is. And if I evaluate it, it says the occurred 97 times, off 68 times, and it's sorting nicely by the frequency of the occurred words, right? Now let's do it all together for George Washington and Barack Obama. So this is essentially for George Washington, right? If I if I, uncomment that, but let's just do it for Barack Obama right now, because that's 2016-01, January 12th. And Barack Obama said the word 264 times compared to George Washington, the use of definite articles. But, of course, we don't know how long his speech was and things like that. So I don't want to get too carried away with interpolation, right? So, but that's the idea. So now at least we have a very similar, controlled regular expression space and frequencies to play with. Okay. So now what about reading all the State of the Union addresses at once? So for this, there's another method called whole text files. So whole text files allows you to read all the text files or files that correspond to a pattern. So in this case, I use star.txt, and I'm pointing to this directory SOU. So this SOU all is going to read all the text files. Okay, and I've cached it now. So all the State of the Union addresses are there in SOU all. SOU all is now an RDD. So what is this RDD? It's an RDD of string, comma string, where the first string is just the file name. The second string is the content of the file. So this is quite convenient for small files like this one. Okay, so now I can do SOU all.count and find out how many files there are. And now this is the first time I'm actually taking an action. Remember, all of the stuff above is lazy. Nothing's happened. Now actually it's happening. So it's taking through that data, and it's going to probably take a few seconds depending on how many people are also pressing it.
Cache lazy as well.
Yeah, it caches lazy the first time. Yeah, exactly. Yeah. So then it's 26.97 seconds. If I do count again, right, the control enter and do count again, this should happen a lot faster. But it's complicated because we're all sort of crowding on the same cluster. So it happened in 0.07 seconds, right? But it didn't happen that quickly, right, in real time, because other people are probably clicking in. Okay, so that's because we have cached it. So now let's examine the first two elements of the RDD, SOU all, right? So I'm just going to take. And when I take, what I'm seeing is I have the file name, like I said, distributed file system, dataset SOU, and then the string. You see this is one huge string starting here with George Washington, and the string should continue all the way to the bottom. And I don't know. Oh, strange. Okay, I can go down. So this is one. The second element is basically one whole string. See, it ends here. Oops. And then that's the the second element of the first element. This is the second element in this RDD string, right? This is the second file name, and then this is the contents of his next year's address, and so on. So now clearly all the elements are a pair of strings. So what we now can do is just look at the file name. So if I do file contents pair, if I call the elements of SOU all file contents pair, and then I just map it to file contents pair ._1. So ._1 is Scala notation for the first element of a tuple. Okay. Oh, sorry. First element of a tuple. So now this should give me, after collect, it just gives me the names of all the files because it's just the first elements, right? And then this is essentially, let's find out the number of words in each of the State of the Union addresses, right? And this, I just did this because it's a trick. You have to be very careful because now we're working with strings inside the closure, right? So what I mean is when I do SOU all.map and I take the file contents pair, and then if you look at what I'm mapping it to, here's my full closure here. So let's examine that a bit. So here you see file contents pair ._2 is the string that is the content of each file, right? So I need to now start parsing that. I can use the same replace all and blah, blah, blah. These are all the string methods, right? So I can do all of that, but these are all string operations and I can split. This is all fine. But I have to do dot size because at the end of it, when I split it, it gives me a Scala array of strings, right? Separated by white spaces with all my hacks. And then the size gives me the length of the array. So inside the closure, I'm actually working with one string, right? So if I shift enter, that's again done. And then I have to actually evaluate it, right? That's lazy. So this is basically the number. What is this exactly? This is the number of words, right, in Yeah, yeah, without punctuation. So you can see Obama's, kind of talks a lot. I mean, people have been starting to talk a lot, I think. I mean, okay, this is where you have to do some statistics and interpretation, but this is a silly example. But
The first one is 1,000 letters.
yeah, it might be steadily increasing. I don't know. I just made this while I was at the seminar just now, so I have no idea.
In the middle, there are 25,000.
Oh, really? No.
25,000.
Yeah, in the middle.
Oh, that must be World War II, maybe, or who knows what.
Did they have that much time to talk during?
I don't know, man. Okay, so this would be a good project. I have no idea. Maybe that's not what, I don't know what it is. Okay, so please look at this homework examples here, the sort by, and some other things you can play around with. And we'll see you next week.